Hello friends, welcome back to my YouTube channel. In this class I am going to discuss some more problems of chapter 7 of PKNAG's Engineering Thermodynamics book, which are based upon the concept of entropy. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. You see, the question number 7.4 is like this. In a Carnot cycle, heat is supplied at 350 degrees Celsius and rejected at 27 degrees Celsius. So this is your source temperature and this is your sink temperature in a Carnot cycle. The working fluid, which is water, which while receiving heat evaporates from liquid at 350 degrees Celsius to steam at 350 degrees Celsius. The associated entropy change is 1.44 kilojoule per kg Kelvin. If the cycle operates on a stationary mass of 1 kg of water, how much is the work done per cycle and how much is the heat supplied? And in the next bit, if the cycle operates in steady flow with a power output of 20 kilowatt, what is the steam flow rate? So first, you see, in a Carnot cycle, which is a reversible cycle, consists of 4 reversible processes. Reversible process, the characteristic of which is one of the causes of reversible process, or one of the example of reversible process is the process in which the heat transfer takes place with infinitesimal temperature difference. If the temperature difference is finite, the process is irreversible. In this case, the source temperature is at 350 degrees Celsius, or in terms of Kelvin, that is 350 plus 273, that is 623 Kelvin. 623 Kelvin. This is source temperature. But whatever heat is supplied to heat engine, you see, this is the heat engine inside which there is some working fluid which completes a cycle, and in this case it is given that the working fluid is water, which while receiving heat, when heat is supplied to water, it gets converted into water vapor, that is your latent heat, and during this process temperature remains constant, and that temperature is constant at 350 degrees Celsius, because it is given that while receiving heat, water evaporates from liquid at 350 degrees Celsius to steam at 350 degrees Celsius. So in this case, you see, heat is transferred from this reservoir, which is at a temperature of 623 Kelvin, and here at the receiving end, heat is received by water, which is also at 350 degrees Celsius or 623 Kelvin. So temperature difference is not there. So it is a reversible heat transfer process. So, and similarly also heat is rejected here to a sink, which is at temperature of 27 degrees Celsius or 273 plus 27, that is 300 Kelvin. This is the sink. This is source, thermal energy, high thermal energy reservoir. This is low temperature thermal energy reservoir. This is sink. That means no matter whatever heat you may extract from this reservoir, its temperature remains constant, and no matter whatever heat you may supply to this low temperature reservoir, its temperature will not increase. and if the associated entropy change is 1.44 kilojoule per kg Kelvin. Obviously when heat is supplied to something means its entropy increases. In this case also the same thing happens. When heat is supplied from the source to water inside the heat engine and water gets evaporated into water vapor, and during that process entropy will definitely increase. Entropy of water increases. On the other hand, entropy of source decreases. Whatever amount of entropy increases, whatever amount the increase of entropy of water is, the same is the decrease of entropy of this thermal energy reservoir also. So you see, the associated entropy change is given delta S of water, change in entropy of water, is given to be 1.44 kilojoule per kg Kelvin. So delta S of water is nothing but Q1, and this is also equal to, this delta S of water is also equal to minus delta S of thermal energy reservoir 1. This is your thermal energy reservoir 1 source. So source का thermal energy entropy of source decreases while entropy of water increases, but by same amount. Whatever is the increase in entropy of water, same is the decrease in entropy of this high temperature thermal energy reservoir or source, which is at 350 degrees Celsius. So delta STR thermal energy reservoir 1, that is source, is equal to minus 1.44. ओनली साइन का डिफरेंस है, क्योंकि एंट्रोपी जो है वाटर का इंक्रीज हो रहा है एट द सेम टाइम जो थर्मल एनर्जी रिजर्वर और सोर्स का डिक्रीज हो रहा है, इसलिए माइनस साइन वी हैव टू पुट बिफोर दैट, बट द मैग्नीट्यूड विल रिमेन सेम. So this is equal to minus Q1 divided by थर्मल एनर्जी रिजर्वर का कितना डिक्रीज इन एंट्रोपी हो रहा है, तो माइनस वट एवर इट इज रिजेक्टेड बाई सोर्स, बट टेम्परेचर चेंज इन एंट्रोपी इज नथिंग बट द इंटीग्रल ऑफ डी कट क्यू बाई टी होता है ना यहाँ, लेकिन हीट लिबरेट हो रहा है और हीट रिजेक्शन हो रहा है, तो माइनस साइन वी हैव टू पुट माइनस साइन बिफोर दैट. So minus Q1 divided by 623, temperature in terms of Kelvin. This is given to be minus 1.44. So यहाँ से अगर हम ये लिखेंगे Q1 आएगा 623 multiplied by 1.44. Q1 is equal to 623 into 1.44. Obviously this Q1 is the heat supplied. This is equal to 897.12 kilojoule per kg. This is the heat supplied to, this Q1 is heat supplied to water. यही पूछा है ना, इफ द साइकिल ऑपरेट्स ऑन ए स्टेशनरी मास ऑफ 1 kg ऑफ वाटर, हाउ मच इज द वर्क डन पर साइकिल एंड हाउ मच इज द हीट सप्लाइड. सो हीट सप्लाइड वी आर एबल टू फाइंड आउट नाउ, एंड हीट सप्लाइड टू द वाटर इज नथिंग बट योर 897.12 kilojoule per kg mass of water. This is the amount of heat supplied. So now we have to find out net work or work produced, work output. We know that this is a Carnot cycle, and efficiency of Carnot cycle is nothing but 1 minus T2 divided by T1. Efficiency of Carnot heat engine or any reversible heat engine is nothing but 1 minus temperature of sink expressed in Kelvin divided by temperature of source expressed in Kelvin. This is equal to 1 minus 300 divided by 623, and this is again equal to work output divided by heat supplied. Efficiency का जो basic definition है work output divided by heat supplied. What is the net work output from heat supplied? That is what the efficiency measures. So from this equation, work output will be nothing but Qs multiplied by 1 minus 300 divided by 623. This is equal to Qs is nothing but here Q1. Qs is nothing but here Q1. Heat supplied is same as Q1. So this is equal to Q1 we have already calculated 897.12, 1 minus 300 by 623. This is coming out to be 465.12 kilojoule per kg. So this is the work produced, work output. This is the work done per cycle. That is 460 per 1 kg of water. 465.12 kilojoule per kg. And the next bit is, if the cycle operates in steady flow with a power output of 20 kilowatt, what is the steam flow rate? What is the steam flow rate? अगर ये steady flow device steady flow manner में काम करेगा, तो अगर flow is steady one, then what will be the mass flow rate of steam? You see, suppose पावर जो टोटल पावर प्रोड्यूस्ड होता है ये होगा इज इक्वल टू गिवन टू बी 20 किलोवाट. पावर प्रोड्यूस्ड इज 20 किलोवाट. पावर प्रोड्यूस्ड मतलब वर्क पर यूनिट टाइम. सो दिस इज वर्क पर यूनिट टाइम, बट वर्क पर यूनिट मास we have already calculated, and it is per unit mass of steam. What is the work produced? That is 465.12 kilojoule per kg. So power is rate of work output. So work done per time is work done per mass in multiplied by mass per mass flow rate, or you can say mass per unit time. mass flow rate of steam ये होता है mass per time. So if you are to find out mass flow rate of steam, this is m dot s. So m dot s I can calculate. This is power produced is given to be 20 kilowatt. Work done per mass is 465.12 kilojoule per kg. This is coming out to be 0.0429 kg per second. This is the mass flow rate of steam. पर सेकेंड में इतना स्टीम फ्लो कर रहा है. ये स्टडी फ्लो में जब जाएगा, ये बॉयलर है, यहाँ से आके टरबाइन को आएगा, ये स्टडी फ्लो के साथ काम करेगा. यहाँ मास फ्लो रेट विल रिमेन द सेम थ्रू आउट द 4 कंपोनेंट, बॉयलर, टरबाइन, कंडेंसर, and then it will go through pump again to boiler. But whatever mass flows, it remains same, because it is one of the properties of steady flow processes. Mass flow rate remains constant according to principle of mass conservation. So this mass flow rate of steam is going to be 0.0429 kg per second. So next question is, a heat engine receives reversibly 420 kilojoule per cycle of heat from a source at 327 degree Celsius. 327 degree Celsius. और यहाँ हीट जो आ रहा है सोर्स से 420 किलोजूल पर साइकिल, and the source temperature is at 327 degrees Celsius, and rejects heat reversibly to a sink at 27 degrees Celsius. Sink temperature दिया हुआ है. There are no other heat transfers for each of the three hypothetical amounts of heat rejected. So there are three heat rejection amounts given in the question, and you have to find whether the cycle is reversible or irreversible or impossible. And we have to conclude from Clausius inequality. Clausius inequality is valid only for cycles, and using that Clausius inequality we can conclude whether the given cycle is reversible or irreversible or impossible. Here the source temperature is given to be 327 degrees Celsius. This is 327 degrees Celsius. If we want to convert that into Kelvin, that will be 327 plus 273, 600 Kelvin. And this amount of heat Q dot H is 420 kilojoule. And this is going to a heat engine, and this is suppose work output, and this is the heat rejected. This is in fact in terms of energy, so this is QH and this is W net, no dot is required. This is not given in terms of power, it is given in terms of energy. So QL, according to QL, the integral of del Q by T will be calculated. Cyclic integral of d cut Q, Clausius inequality says that the cyclic integral of del Q by T or d cut Q by T is going to be less than or equal to 0 for any cycle. And if cyclic integral of del Q by T is less than 0, the cycle is irreversible. Cycle is irreversible. And if cyclic integral of d cut Q by T is equal to 0, then the cycle is reversible. And if cyclic integral of d cut Q by T is greater than 0, the cycle is impossible. So cyclic integral of del Q by T or d cut Q by T is nothing but QH per TH. When heat is added to a cycle, it is taken to be positive, and when heat is rejected from cycle, here heat is rejected from cycle, that is QL. Heat added to the cycle is QH. So that is positive sign is placed before QH, but negative sign will placed before QL because heat is rejected from the cycle to the low temperature reservoir, that is sink. And finally it becomes QH by, this is your cyclic integral of dq cut Q by T. This is equal to this much, QH by TH minus QL by TL. This is your cyclic integral of del Q by T or d cut Q by T. So this is the condition according to Clausius inequality. So by determining the cyclic integral of d cut Q by T, we can conclude. So first, the heat rejected is given here 210 kilojoule per cycle. So what will be the cyclic integral of d cut Q by T for case A? dq by cut Q by T is equal to QH upon TH minus QL upon TL. This is going to be is equal to QH is constant for 3 cases and it is given to be 420 kilojoule per cycle. This one is given 420 kilojoule per cycle at temperature. TH is also given, TL is also given, but QL will vary in 3 cases. So QH upon TH is 420 divided by TH is 600 minus, in case A, heat rejected is 210 divided by temperature is this temperature, low temperature is given to be 27 degrees Celsius, that is 300 Kelvin. So 300. The temperature of sink is given, it is constant at 27 degrees Celsius. So this is equal to, it is 0. So since the integral of d cut q by t is equal to 0, the cyclic integral of d cut q by t is 0, so the cycle is reversible. Cycle is reversible. The cycle is reversible. Similarly, for B, the cyclic integral of d cut q by t is equal to qh by th. Qh by th, again the formula remains same, minus ql by tl. This is equal to 420 by 600 minus 105. This one, 105 kilojoule per cycle rejected in case B. 105 divided by 300. This is equal to 0.35. This is greater than 0. So this cycle is impossible. Cycle is impossible. Impossible. Then bit C के लिए, C, when the amount of heat rejected is given to be 315 kilojoule per cycle. Here in the case C, it is given that the heat rejected is 315 kilojoule per cycle. So cyclic integral of d cut q by t is equal to qh upon th minus ql upon TL. This is 420 by 600 minus 315 by 300 is equal to minus 0.35. Since this is less than 0, since this cyclic integral of d cut q by t is less than 0, the cycle is irreversible. Irreversible. So next question is question number 7.6. You see, in figure ABCD represents a Carnot cycle. You know, Carnot cycle consists of two reversible isothermal processes and two reversible adiabatic process. In this case, ABCD is a Carnot cycle on PV diagram, and AB and CD are two isothermal processes, and BC and AD or DA are reversible adiabatic processes. T1 is again greater than T2. The oval figure, this oval figure is a reversible cycle where heat is absorbed at temperature less than or equal to T1 and rejected at temperatures greater than T2. यहाँ देखो, यहाँ जब टेम्परेचर होता है ये सेम होता है, लेकिन व्हाट अबाउट दिस हियर? Here the heat rejection during the process CD in case of oval cycle takes place at a higher temperature than that in case of Carnot cycle. In case of Carnot cycle, at this temperature T2, the heat rejection takes place. So when where heat is absorbed at temperature less than or equal to T1 and rejected at temperatures greater than or equal to T2, prove that the efficiency of the oval cycle is less than that of Carnot cycle. You see, both are reversible cycle, but we have to prove that the efficiency of oval cycle is less than this efficiency of ABCD, the Carnot cycle. You see, efficiency of any reversible cycle efficiency of any reversible cycle is 1 minus sink temperature divided by source temperature. Of course, these two temperatures are in terms of Kelvin. So in this case of in case of Carnot cycle A, B, C, D, the efficiency is this much, because during this CD the temperature remains constant at T2, and AB, during the process AB, heat addition takes place at a constant temperature T1, and during the process CD heat rejection takes place at constant temperature T2. So this is the efficiency. But what about the oval cycle? In case of oval cycle, the heat rejection takes place at a temperature greater than, suppose I will consider two cases, one is for greater than and one is for equal to. So whenever this temperature at which heat rejection takes place in oval cycle, the temperature at which the heat rejection takes place is greater than T2, and heat addition, the temperature at which heat addition takes place is suppose less than T1, then obviously the whatever efficiency will, since it is also a reversible cycle, that is efficiency of oval cycle will be 1 minus T2 plus something divided by T1 minus something, suppose delta T. And if you calculate, this one will be higher than this one, because suppose T1 is 300 Kelvin, T2 is, suppose T1 is 600 Kelvin and T2 is 300 Kelvin. So what is the efficiency of Carnot cycle, that is ABCD, will be 1 minus 300 divided by 600. It is going to be 0.5 or 50%. But what about the oval cycle? Suppose in case of oval cycle, T2 dash means temperature at which heat rejection takes place in case of oval cycle. It is obviously going to be greater than T2. Suppose it is 350 Kelvin, and T1 dash, temperature at which heat supply takes place in oval cycle, T1 dash, suppose 550 Kelvin, less than 600 Kelvin. Then what will be the efficiency of oval cycle? Is equal to 1 minus 350 divided by 550. It is going to be 200 divided by 550. So it is obviously be less than 50%. It will obviously be less than 50%. So efficiency of oval cycle is going to be less than efficiency of Carnot cycle when these temperatures are, there are some differences, and insofar as the temperatures at which heat addition takes place and temperature at which heat rejection takes place are taken into consideration. Supposing that during this part of cycle, you see temperature remains constant, here also the temperature remains constant. Suppose that the same temperature heat addition takes place in both the cases, then obviously this area represents included area. This total included area represents net work output, and for cycle ABCD this is the total included area, but for the oval cycle this one is the included area. So if for the same heat input, if temperature at which heat addition takes place remains same, obviously the heat supply also remains same. So if for same heat input, if there is some more work output in case of a cycle, then obviously the efficiency of that cycle will be higher than the other one. So here efficiency of ABCD, that is the Carnot cycle, will be higher than the efficiency of oval cycle. So thanks for watching.